This cross-section shows the various fluxes in an idealized hydrogeologic system. Up to this point, we've really been focused on understanding the basic concepts associated with these fluxes, but now we want to turn our attention to understanding how we might simulate these fluxes and gain a quantitative understanding of how the water is moving in the subsurface. So to do this, we have, even though it's an idealized system, a fairly complicated system. We've got a lot of water moving around in different directions, a lot of different processes going on. And so in order to come up with our first attempt at some simulation, we need to simplify this system even further. And so one of the things we can do is recognize that this sketch, which we've been seeing now for several classes, this sketch is vertically exaggerated. So the scale in this direction is greater than the scale in that direction. And we do that for convenience because we want to be able to see what's happening. But if we were to draw this where the scale is 1:1, where it's a true scale, it would look something like this, where it's really now quite thin compared to its overall length. And one of the things that we see when we do this is that the groundwater flow paths, shown here, mostly are going horizontally. There still is a vertical component, they're still moving downwards, and then upwards to discharge at the streams, but it's really quite small compared to the overall horizontal extent. And so what this will allow us to do is to, at least at first, ignore the vertical variations and just simply assume that we have horizontal movement of the groundwater. So what that means is that we take this system, which is what our idealized model really looks like, and we'll assume that it looks like this, where I'm going to introduce a confining unit here, this layer here, and assume that the water flow within the aquifer right here is what we're interested in, and it's simply flowing horizontally as shown by these blue arrows. So we'll have recharge coming in through this confining unit as shown by these arrows and the label R, and then we have groundwater flow horizontally shown by these light blue arrows and discharging to the stream over here. Okay, so this will be our simplified idealized model, and we want to come up with a way to predict the hydraulic head, which is shown here and measured here. And so we want to predict what the hydraulic head distribution is in this aquifer, and also what the flux is and how it's distributed. Our goal is to predict the hydraulic head and the groundwater flux. And in order to do this, we have to draw on our understanding on how these processes work. And we'll take this understanding and use it to develop the equations that we'll then solve to make the prediction. So what are the rules? Well, the first one is conservation of mass. We said that this was a rule that we would obey. I think we saw this on the first day of class. And if we can assume that the density of the water stays constant, then we can go from conservation of mass to conservation of volume, and we can do an overall water balance. So we can assume safely, I think, that conservation of mass is one of the rules. And also we can assume that the groundwater will behave Darcy's law. This will be the flow law that we'll assume is governing the flow through porous media. And then finally, the third assumption is that the simulation allows us to bring in aspects of the field setting that we're interested in particular the boundary condition and parameters like hydraulic conductivity and storativity, and perhaps also the thickness would would be parameters that we would consider in the model. All right, so the first thing that we need to do is to assume that we have this water balance or conservation of mass. And the approach that we'll use to implement this is the same approach that we used at a larger scale, and that is that we'll assume a region over which the volume or over which the balance is going to take place. This region we sometimes will call a control volume. And so if this is the sketch for our problem, we'll put in the control volume as a little block like this. And this is a cube, say, or it's going to be a three-dimensional cube. The third dimension will be going back into the page, and that will be just assumed to be a unit length. Okay, so there's the block, and we're going to pull that block out, and we're going to conduct a balance on it. So the balance is here. This is the same one that we've used in the past, where we say that the volumetric rate into the control volume is equal to the volumetric rate out plus the change of the volume stored with time. Okay, so we assume that that's going to hold, and then we go and look at the individual components. Well, the volumetric flow rate in is here, and what I want to do is write that in terms of flux. So I'll have a flux that comes in like this, and so the volumetric rate in is simply equal to the flux in times the cross-sectional area, which is dy times b. And so that little delta, that's a unit width in this direction, and then b is the aquifer thickness, or the dimension of our control volume in that direction. So that's the cross-sectional area like this, and the flow rate, this flux coming in, is perpendicular to that area. Okay, so that looks good. And then the flow rate out is simply the flux out times the same cross-sectional area. And then we also want to have some flow coming in from recharge. So there's the recharge flux, and we're going to have recharge flux times this cross-sectional area to give us a flow rate. So that's going to be R times delta x delta y, which would be, there's delta x and delta y. Okay, and the last term is the change in volume stored with time. And what we're going to do is write that like this. And we can see if we do, if we kind of cross out that term there, and then this is an area, and this is the same area, then we have the change of the volume stored with time. So the units look good, but what we can do here is, by writing this, I've written this in a special way, because this thing here says the change in the volume stored per area per change in head. So we recognize that as the storativity. So that term there is that term there. And then delta H, delta T, this is just like an incremental delta, but we let that increment get small, and it just becomes the derivative here, dh dt. And then these are these two incremental lengths, delta x and delta y. Okay, so the rate of change of volume stored here becomes this, and we substitute in this one goes here, this one goes here, and this one goes here, and this stuff goes there. Okay, so this is then an expanded version of the volume balance. Okay, so this equation here is the one that we just ended up with. And what I want to do is recall from the Taylor series that the flux going out of this block is equal to the flux coming in plus this delta Q, which is the small change in flux that happens from inlet to outlet. Okay, so I think this is pretty easy to understand conceptually. And then this small change in flux we simply write like this, as the gradient in flux in the x direction times this small increment in length, delta x. And we can think of this conceptually as that delta x in the derivative canceling with that delta x and giving us a delta q. Okay, so we can I think convince ourselves that this is okay by doing that. But what we want to do is introduce this derivative and this delta x. Okay, so what we're going to do now is to take this term here, and that's q out is right here, and so I'm going to take this stuff and substitute it in there. Okay, and that's what happens when I do that. All right, so now I can cancel out this times qn with that. So this goes and this goes. And then I'm going to take this and multiply through. So that term is right here. This is right here. And that is right there. And so then what we can do is continue to cancel out these delta x, delta y. They appear in all the terms like that. And that leaves us with this. Okay, so recall that this was the water balance, or the mass balance, or the volume balance. Q in equals Q out plus change in volume stored. We wrote it in terms of flux, and this is what we end up with. The recharge equals the gradient in the flux times B plus the storativity times dH dt. Okay, so that'll be an important equation. Essentially, it's the volume balance. There we go. And in this form, I guess I'm going to shuffle it around and bring this dq dx over on the left-hand side. Okay, so that'll be the form of the volume balance that we'll use. All right, so let's take a look at this equation, this volume balance, and see. It's often a good idea to take a look at equations that you develop and just see if it makes sense intuitively. So what we say is that let's start off by assuming that the problem is at steady state. So that's what I'm calling case 1. So if it's at steady state, then dH dt is equal to 0. So under steady state conditions, that's 0. And if that's the case, then dH dt must be negative to give I'm sorry. Let me get rid of that. So under steady state conditions, then R must be positive. If R is positive, then dq dx is positive. So if dq dx is positive, that means that the flow rate, or the flux here entering, is less than the flux exiting. Okay? So if this is positive, then the only way, basically it means that for the horizontal groundwater flow, there's more flux coming out than is entering. So it must mean that recharge is making up the difference. So if this is positive, then recharge must be positive. So that makes sense. And then we can look at this other case. This is case 2, where assume that the recharge is equal to 0, so we get rid of that. And in this case, here, dH dt must be negative for dq dx to be positive. So if dq dx is positive, that means that we've got more flow going out than coming in. But in this case, we're assuming that recharge is equal to 0. So the only way you could have more flow coming out than in is if water is draining out from storage. So if water is draining out from storage, then the water level is going from here and dropping. And if that's the case, then dH dt is going to be negative. So if dH dt is negative, the head is dropping, we're draining water out. If this is negative, then that sign there makes this side positive, and we get dq dx is positive. Okay, so I think that makes sense. If we're having more water flowing out than coming in, and there's no recharge, then we have to be draining water out of the control volume. So it looks like this thing, even though it at first glance is somewhat cryptic, it looks like it makes sense and is consistent with how we would view this on an intuitive basis. Okay, so the next step here is to introduce the flow law. Here's Darcy's law, and we're going to take this and substitute it into the volume balance. So here's the volume balance, and the flux appears here. So we're going to take this and put it in there. And that will give us then a result shown here that is really the combination of two things. It's the volume balance and Darcy's law. So it has those two concepts together. And we get this form. Oops. So this then is pretty important. This has the two main concepts for groundwater flow, and this will be the governing equation for the heads in an aquifer. And this is the one we just developed, but we can do this several different ways. What we just did was really only considered flow in 1D. But we could do this for a 3D case, in which situation this is in the x direction. So there's that term. But if we do it in 3D, there's a similar term for flow in the y direction and flow in the x direction. And the right hand side is the same. Okay, so if we go from 1D to 3D, we get this as the governing equation for the problem. We can modify it further and say that the hydraulic conductivity is different depending on what direction the flow is. So this is an anisotropic condition, and Kx is the hydraulic conductivity in the x direction, y direction, and z direction. And so for a 3D confined aquifer that is anisotropic, this would be the governing equation. The right hand side is the same, and really all we've done is replace the equation above it with this one that has these subscripts that indicate the direction of the hydraulic conductivity. And this equation here can be rewritten like this, where this means the gradient of h, and this del, there should be a little dot there because it's the divergence. So this del is the gradient operator, and it allows us to write this equation, the left hand side of this equation, just simply in a more compact form. Okay. So sometimes you'll see the equation written like that in papers or textbooks. All right, so now we can go and simplify. Well, I'm going to go back here to this 1D version, and I'm going to say, well, okay, what about in this case we have a steady state version. So if it's steady state, the dH dt is equal to 0. And then I get everything else, and I get that version. So this is for a 1D confined aquifer that's isotropic and at steady state. That's what we just did by setting that term equal to 0. It's heterogeneous, and the reason you can tell that is because this hydraulic conductivity term is inside of this derivative. Okay, if both of these are functions of x, if hydraulic conductivity is changing with x, then it needs to stay inside here. If it's constant though, then it'll come out of the derivative. So if it's the hydraulic conductivity is uniform, then the hydraulic conductivity comes out, and this is written like that. And then the next thing we can do is realize that this is the gradient of the head in x, and this is the gradient that operates on the gradient, and that is the second derivative when you have the gradient of a gradient. So this thing here we can write like that. So this last form is the simplest of all. This is the case where we have a 1D aquifer. We assume that it's confined. There's recharge, but it's isotropic and homogeneous. So the hydraulic conductivity is the same over the whole domain. So this is the simplest version, and indeed this then is the governing equation for the idealized situation, the idealized scenario that we saw on the first slide. Okay, so here's that simplified equation. This is the governing equation, and we see that we have this second derivative here on the left-hand side. So the second derivative, it's going to be an important term for understanding the distribution of hydraulic head. Recall that the second derivative is going to be proportional to the curvature, and so these lines would have second derivatives, say this one here, and the second derivative is going to be greater for this one than for this one because the curvature is sharpest right there. So the second derivative would be highest right there, and then places like this where the curvature is pretty low, the second derivative would be much less. So the magnitude of the second derivative we associate with the curvature of of a line, and also this will have different signs. So when we have a curvature that looks like this, that's a positive second derivative. That's positive. This is negative, and this is negative. This is a larger negative number here than here. And then these guys, these are all examples of the second derivative of these examples is equal to 0. And that's because they're straight lines. They have this one, the first derivative is 0, the slope is 0. Here the slope is not 0. This would be a positive slope, but it's a second derivative that's equal to 0. So yeah, here's the animation. This is second derivative greater than 0, second derivative less than 0, second derivative equal to 0. And we can then come up with some implications here, because where the second derivative is greater than 0, then this is positive, and where this is positive, then the recharge had better be negative, right? Because recharge needs to be negative to cancel out that negative sign. Okay, so if the recharge is negative, that means that water is discharging out of the aquifer. Okay, so in places where we have the water table looking like this, then we can infer from this equation that the recharge has to be negative or it's a discharge point. And in fact, we might assume that this is a stream. If we draw it out, let me draw out a kind of a cross section. So if this is a water table, the stream might be right here, and that would be a point where the second derivative was greater than 0. Similarly, where we have a second derivative that's less than 0, we've got a mound like this, and this means that there would be positive recharge. This is negative here, so r can be positive. So r greater than 0 indicates recharge, and then where the water table forms a straight line, that means that the recharge is equal to 0. There's neither recharge nor discharge. Okay, so what we've done so far in developing this equation and the various other versions of this that we saw a couple of slides ago is we've used two of our assumptions, the conservation of mass and the flow law, and we substituted one and the other to get this governing equation. And what it's telling us is that the curvature of the head profile depends on the recharge rate scaled to the transmissivity. So curvature depends on this, recharge scaled to the transmissivity. And recall, transmissivity of an aquifer is the hydraulic conductivity times the thickness. Okay, so what this is the governing equation. What this is telling us is kind of the rules that the head has to obey. But it doesn't really tell us what the head actually is. So in order to do that, we need to have additional information. And for that, we go back to our problem. And the way to think about this is that this governing equation says how the head distribution has to vary, the rules that it has to obey. But we need some more information to determine what the head actually is, and that information will come in the form of boundary conditions. And we can think of this as additional information or perhaps additional equations that have to be satisfied. So for this problem, one piece of information that we have to have satisfied is that the flow right here, we're assuming that this is a groundwater divide, and so the flow right here is equal to 0. And if the flow is equal to 0, then the head gradient is going to be equal to 0. So the head gradient in the x direction is equal to 0 at x equals 0. Okay, so this thing here, this is a boundary condition. It says how the head is behaving at this particular boundary. On the other side, we have a boundary condition over here, and we have a stream on this side, and we are assuming that the head in the aquifer is equal to the head in the stream. So the head in the stream is H1, and so in order for that to, in order for our assumption to be satisfied that the head in the aquifer has to equal H1, the head in the stream, at x equals L. So L is this. So when x equals L, we're out here, and the head in the aquifer has to equal H1, the head in the stream. Okay, so this is another boundary condition. What we've done is used two different types of boundary conditions. One where we specify the head at the boundary, one where we specify the head gradient at the boundary. So in general, to solve these problems, what we need to do is look at the problem, and based on the various aspects of the hydrogeologic conditions, we're going to select a governing equation that is appropriate. If it's a 3D problem and we're interested in how the heads vary with x, y, and z, then we would need to have a 3D governing equation like we saw a couple of slides ago. So we would select the right form of the governing equation. This form here is valid for 1D homogeneous steady state problem. And then the next thing we have to do is determine what the boundary conditions are that follow from the conceptual model for the problem. So the boundary conditions will be something that we determine from the sketch of the problem that we've developed. Okay, so here is the overview of what we need to do. We need a conceptual model that's simplifying field conditions. Generally, we'll develop a sketch that shows the simplified version of the field conditions. We select the governing equation and the boundary conditions that are appropriate for the conceptual model. Then we solve the governing equation, and we need to include the boundary conditions in the solution. Okay, so this is the overall approach. We've come up with, we've developed the governing equation and we've selected the boundary conditions. So the next step is to be able to solve the governing equation.